Hey, welcome everybody. So in this video, I'm going to work through some practice problems with you, and then you guys are going to be responsible for answering the questions on the back of this paper, okay? So in stoichiometry, you guys are going to relate an amount of one substance to an amount of a different substance. And it all comes from a chemical equation, okay, which is provided to you on the front of this worksheet. You also need your periodic table because you're going to often have to use molar mass, okay? So looking at this, the first type of problem is a mass-to-mass stoichiometric calculation. If I read the problem, it says if I decompose 10 grams of NaHCO3 solid, how many grams of H2O gas will be produced, okay? So the first step in stoichiometry, which we went over today, was to make sure that you have a balanced chemical equation. Okay, and we already do for this one. It's been provided to us. Step 2 was to identify your known amount, which is right here, it's this value here, and what it is that you're trying to calculate. So we actually need to figure out how many grams of H2O. So we need to calculate grams of water. That's our wanted value. Next step, come up with the mole ratio. Okay, so let me think about this. We're starting off with NaHCO3. We are making water, okay, as one of our products. And that's the one that we've been asked about in this particular problem. So if I look at the equation, for every 2 moles of NaHCO3, sodium bicarbonate, that I start with, we produce 1 mole of water. So my mole ratio is going to be 2 moles of NaHCO3 for every 1 mole of H2O. Okay, so there's the mole ratio. It just comes from the coefficients in the balanced chemical equation. And the only 2 things that you include are the coefficient for your known substance and the coefficient for your wanted substance. You just compare those in the mole ratio, okay? All right, the next step, after you've identified known and wanted, compared them using a mole ratio, you actually need to start setting up your problem. So if we look at this mole map, we're starting here with grams, and we want to end up with grams. So if I follow this map from here to here, I actually touch 3 different conversion factors. I'm going to use the molar mass, mole ratio, and then the molar mass of the wanted substance. That's the order and the coefficients that I'm going to have to put in my dimensional analysis. Remember that you start dimensional analysis always with your given. Okay, and just like we've been doing for a long time now, you write down your given amount, drop the unit. Okay, now we're using the molar mass of this substance, which comes from the periodic table. If I add together sodium, hydrogen, carbon, and 3 oxygens, I actually get the number 84.006. I kind of ran out of room, but that's the number that goes on the bottom. And that is equal to the mass of 1 mole of NaHCO3, sodium bicarbonate. Now, I got to keep going, so let me go ahead and drop down the unit, just like always. On my mole map, after the molar mass of my known substance, it's time for the mole ratio. So I just need to fill in this information. 2 moles of NaHCO3 will produce 1 mole of water. And I need to keep going, so let me draw a line and drop that unit down. The last thing that's in my mole map is the molar mass of my wanted substance. So 1 mole of water is equal to the mass of 2 hydrogens and an oxygen. So that's it. My unit should cancel out. Grams, gone. Moles of NaHCO3, gone. Moles of water, gone. The only thing I have left is grams of H2O. That's the only thing that didn't cancel out. And that's what I was asked to calculate, so I've set this up properly. All we need to do now is multiply across the top. So 10 times 18.015. And I get 180.15. Then we take that value, well, we first multiply the bottom. So 84.006 times 2, and I get 168.012. So then the last step is to take that product from the top and divide it by the product of the bottom. In our given amount, we had 3 significant figures, which means I get to keep 3. So this answer is going to be 1.07 grams H2O. That's 3 significant figures, okay? All right, next problem. If the reaction yields 10 grams of CO2, so there's my given amount, there's my starting amount, how many molecules of H2O form, okay? So now we have to relate carbon dioxide to water. They're both on the product side, but that's okay. It doesn't really matter. If I look at the equation, for every 1 H2O, we also produce 1 CO2. So my mole ratio is 1 mole of CO2 for every 1 mole of H2O. So it's a 1-to-1 mole ratio, okay? Again, always check your map. We're starting with grams again. We're going to have to use molar mass. We're going to have to use a mole ratio. But since we're trying to calculate particles, at the end, we're going to end up using Avogadro's number. So just start setting up your problem. Start with your known. Draw your lines, drop your unit. Now the first thing on my mole map was the molar mass of carbon dioxide. So that's carbon plus 2 times the mass of oxygen. Which I got 44.009. That's equal to 1 mole of CO2. So the molar mass is done. After that, I need to include my mole ratio. Drop your unit. Our mole ratios for every 1 mole of carbon dioxide, we get 1 mole of H2O. So I just fill that in. And then the last thing was Avogadro's number. So let me drop down this unit. The way it works is 1 mole is equal to Avogadro's number of molecules. All of our units should cancel out, except for molecules, okay? So, again, we multiply across the top. And I got 6.02 times 10 to the 24th power. And then we divide that by the bottom, which is just going to be 44.009. Okay, we get a big long number. Again, the number that we were given at the beginning had 3 significant figures, so we're going to keep 3. 1.37, we got to round up, times 10 to the 23rd power. Don't forget the exponent. Okay, so there's the answer for this problem. Okay, next one. We are given formula units of NaHCO3. So we're starting here. 2.2 times 10 to the 23rd formula units of sodium bicarbonate react to form blank molecules of CO2. All right, so we got to calculate molecules of carbon dioxide. So we're starting with a known value in particles. We're going to have to use Avogadro's number, mole ratio, and Avogadro's number again to get to wanted particles. Okay, so if I just go from my known to my wanted, those are the 3 conversion factors I'm going to have to use to solve this problem. Always start with your given amount. We know information about formula units of NaHCO3 has to go here. And there's Avogadro's number of formula units in 1 mole of the substance. Drop the unit down. The next conversion factor after Avogadro's number is the mole ratio. So if I look at NaHCO3 in the balanced chemical equation, there's the coefficient 2. So 2 moles of NaHCO3 will produce, let me look at carbon dioxide, 1 mole of carbon dioxide. And then 1 mole of carbon dioxide has Avogadro's number of molecules. Now the good thing about this kind of calculation is that, yes, my units cancel out from top to bottom, but also Avogadro's number cancels out. Because I have the same number on the top and the bottom, it becomes the proportion 1/1, which cancels out. So I don't even have to put that in the calculator. If I have the exact same number on the top and the bottom, it cancels out just like units do. So really, the only thing that's left is my starting amount, and then on the bottom, I still have that coefficient of 2 for my mole ratio. So I'm going to take 2.2 times 10 to the power of 23, that's my starting amount, and divide by 2. And I get 1.1 times 10 to the 23rd. So there's the answer for that one. Okay, so then next problem, we're going to do a mole to mole conversion. How many moles of CO2 are produced? Okay, so we're going to have to calculate moles of CO2. So that's actually my wanted there. Are produced when 4.3 moles of H2O are produced. So we're starting with 4.3 moles of H2O and we're calculating moles of CO2. Now if I use my mole map, if I go from known amount of moles to wanted moles, the only conversion factor along the way is the mole ratio. That's it. So the only thing we're going to have to use is a mole ratio. Well, what is the mole ratio? Let me look up at my coefficients here in the balanced chemical equation. We were given water, so that's a coefficient of 1, and we were asked to find moles of CO2, which has a coefficient of 1. So my mole ratio is 1 mole of H2O for every 1 mole of CO2. Okay, well let me start with my given. Draw my lines, drop my unit. I'm going to go ahead and fill in my mole ratio since that was my only conversion factor. And it looks like our only conversion factor is 1/1. So if you look at this mathematically, we're going to end up with the same number. Except now it describes moles of carbon dioxide. Okay? Mole to mole is really easy because you only have one conversion factor, and it's the coefficients from the balanced chemical equation, the mole ratio. Okay, last one. So this is a moles to mass stoichiometric calculation. Question is, how many grams of NaHCO3, all right, so there's my wanted, decomposed if I collected 2.50 moles of H2O from the investigation? Okay, so we're comparing H2O to NaHCO3. So if I look back at my balanced chemical equation, I produce 1 mole of water for every 2 moles of sodium hydrogen carbonate that decompose. Okay. So my mole ratio is going to be 1 mole of H2O for every 2 moles of NaHCO3. Let me start with my given amount. Draw my lines and drop my unit. If I look at the mole map, since I'm starting with moles, I'm going to go straight to the mole ratio. Okay, so if I start here, there's no conversion factors, just go to the mole ratio. And since I have moles of H2O on the bottom, I'm going to put 1 mole H2O on the bottom and then 2 moles of NaHCO3 on top. But I don't want moles, I want grams. So let me drop down that unit. If I'm trying to get to grams for my final answer, and I just did the mole ratio, I need to use the molar mass of my wanted substance. Okay, so just if I'm going from known moles to wanted grams, I only touched two conversion factors. First was the mole ratio, we did that, and now is the molar mass of the wanted substance. And we already calculated that in a previous problem. Okay, so all we need to do now is multiply across the top, and then we're not going to need to divide by the bottom because both of those numbers are 1. Okay, so I have 2.50 times 2 times 84.006. Okay, and I end up with this number in my calculator, 420.03. We need to keep that to 3 significant figures, so 420 and a decimal point. That makes that last digit a significant figure. Now what I want you guys to do is work on the back of this sheet. If you guys look at the back, you're actually working problems using the same balanced chemical equation. Okay, so just use this equation, use your mole map, use dimensional analysis, and go ahead and answer questions 1 through 5.